Quantum mechanics is really strange. It says some weird things about the nature of the universe. For instance, it says that quantum objects like electrons can exist in a superposition of states. Deep ideas from linear algebra underlie this strangeness. For instance, the states we are referring to actually live in some vector space, and as we've already alluded to last time, superposition is basically a linear combination of states. Physically, that is like saying that a quantum object exists physically in many states at the same time. A particle can be in two places at once. In what sense is this strangeness a consequence of the underlying mathematical nature of the universe? One of the things we are going to learn in this lecture is a particular product in Rn known as the dot product. The definition will be simple, but the consequences will be profound. Even though quantum states live in an infinite dimensional space that isn't Rn, some of the mathematical results we prove for Rn will have very interesting quantum consequences, which we'll see a little later. Last time we saw that Euclidean space Rn has two operations, addition and scalar multiplication, and these allow you to take linear combinations of vectors. There is another kind of product that Rn has called a dot product, which plays an important role in determining when two vectors are perpendicular. You may remember at the start of the course I mentioned that linear algebra has this theme of hidden structure. The dot product is an example of a structure that exists that is not obvious at first, but when you realize you have it, it can tell us all sorts of things. As we do with every new concept, we'll describe the dot product in two ways, one algebraic and one geometric. Suppose you have u and v, two vectors in Rn, with components that are real numbers, u1 through un and v1 through vn. Then the algebraic definition of the dot product of u and v, called u dot v, is the sum of the pairwise products of the coordinates, u1 times v1 plus u2 times v2 plus ... un times vn. We have a shorthand notation for a sum like this. We write sigma ui vi and write I equals 1 below the sigma and n above the sigma. The Greek letter is a capital sigma. It's like the capital S in Greek, and it stands for sum. The letter I represents the index, and the I equals 1 and n tell the reader what are the starting and ending indices of this sum. Let's do an example. If u is the vector 3, 1, 4, and v is the vector 1, minus 5, and 0, the dot product is 3 times 1 plus 1 times minus 5 plus 4 times 0, which is minus 2. Notice that the dot product takes in two vectors and spits out a number. And what does this number mean? As we shall see, the dot product measures how aligned two vectors are. If the dot product is positive, the vectors are pointing generally in the same direction. If the dot product is negative, they're pointing in generally opposite directions. And if the dot product is 0, the two vectors are perpendicular. The dot product arises in physics when talking about quantities like work, which is the dot product of the force doing the work with a displacement vector. The work done on an object is positive when the object moves in the same direction as the force, and 0 if the force is perpendicular to the displacement vector. Let's look at an example in R2 which we can visualize. If u is the vector 2, 1 and v is the vector minus 1, 2, then you can see by drawing the vectors on the plane that they are perpendicular. In linear algebra, we sometimes also use the word orthogonal for perpendicular. These two vectors are orthogonal, and if you compute their dot product, you see that indeed 2 times minus 1 plus 1 times 2 is 0. We can see why the dot product has this curious property by deriving a geometric definition of the dot product. First, we'll need to know some properties of the dot product, which are evident from the algebraic definition. The dot product is commutative, meaning the order of u and v doesn't matter. You can see this by looking at the definition. Notice that if you switch the roles of u and v, you get exactly the same formula, because the ui and vi trade places as well, but the pairwise products stay the same because this is just multiplication of real numbers, and that multiplication is commutative. The next thing you notice is that the dot product is distributive. You should stop this lecture now and verify this by checking that u dot v plus w, expressed in terms of their components, is the same expression you get from doing u dot v plus u dot w. Third, if you scale one of the vectors, the dot product scales the same way. Cu dot v is the same as c times u dot v. Again, you should check this. Note that if you dot a vector with itself, you get a sum of squares. And the great thing about a sum of squares is that it's never negative, and it's only 0 for the 0 vector. We define the magnitude, or the length of a vector, by taking the square root of u dot u. This notation for magnitude is double bars around the vector. For example, the magnitude of the vector 3, 1, 4 in R3 is the square root of the quantity 3 squared plus 1 squared plus 4 squared, which is the square root of 26. You'll note the square root of the sum of squares is just the usual Euclidean length derived from the Pythagorean theorem. And when we have a new concept, it's good to see how it meshes with earlier concepts. What is the length of a scalar multiple of a vector? Well, from the definition, you can check that the length of 5 times a vector is just 5 times the length of the vector. More generally, the length of c times a vector v is just the absolute magnitude of c times the length of v. What about the length of a sum of vectors? In general, it's not the sum of their lengths because the vectors may not be pointing in the same direction. But by drawing the triangle formed by v and w and v plus w, we can see that the length of v plus w must be less than or equal to the sum of the lengths of v and of w. And this inequality has a special name. It's called the triangle inequality. Now we can derive the geometric formula for the dot product using what we've just discussed. Given two vectors v and w, put their tails together and let theta be the angle between v and w. Notice that the third side of this triangle is just v minus w. From high school geometry, we may remember the law of cosines, which says if a, b, and c are sides of a triangle and theta is the angle between sides a and b, then c squared equals a squared plus b squared minus 2ab cosine theta. So here, the length of v minus w squared is the length of a squared plus the length of b squared minus twice the length of a times the length of b times cosine theta. But by definition, the length of a vector squared is just the vector dotted with itself. So using the properties of dot products, the left-hand side becomes v minus w dot v minus w, which is v dot v minus v dot w minus w dot v plus w dot w. The right side becomes v dot v plus w dot w minus twice the length of v times the length of w times the cosine of theta, the angle between v and w. Canceling v dot v and w dot w from both sides, and using the fact that the dot product is commutative, we see that the left side becomes minus 2 times v dot w, and the right side is minus 2 times the length of v times the length of w cosine theta. We can cancel the minus 2's on both sides and obtain the geometric definition of the dot product of v and w. It is just the product of the lengths of v and w times the cosine of the angle between. This is a geometric definition because it does not involve coordinates. It only involves things we can easily discern from a picture of v and w. Now we learned some things from this interpretation of the dot product. For instance, if you notice that the cosine of an angle in absolute value is always less than or equal to 1, you get what's known as the Cauchy-Schwarz inequality, that the magnitude of the dot product of two vectors is always less than or equal to the product of their lengths. And as theta varies, you see the interpretation of the dot product as a measure of alignment of v and w. If we keep the vector lengths fixed but change the angle theta, the dot product will change depending only on the cosine of theta. So if theta is less than 90 degrees, the cosine will be positive, and if it's greater than 90 degrees, the cosine will be negative. And when theta equals 90 degrees exactly, we see the most important property of the dot product. For non-zero vectors, the dot product is 0 if and only if the two vectors are perpendicular. The if and only if here means two statements are equivalent. Each one implies the other. As a nice application, we can use vectors to give a proof of the geometry theorem that says diagonals of a rhombus are perpendicular. Recall that a rhombus is any parallelogram whose sides are all the same length. So from one corner of the rhombus, form two vectors u and v along the sides of the rhombus. Then u plus v and u minus v are vectors lying along the two diagonals of the rhombus. So if we want to prove that the diagonals are perpendicular, we should hope that the dot product of u plus v and u minus v is 0. So let's check this. U plus v dot u minus v, when expanded using the distributive property, becomes u dot u minus u dot v plus v dot u minus v dot v. The middle two terms cancel because the dot product is commutative. And what remains is u dot u minus v dot v. But this is just the length of u squared minus the length of v squared. And since the lengths of u and v are equal, this expression equals 0. So, in fact, the diagonals of a rhombus are perpendicular. We've seen how to define the dot product now in Rn in two different ways. We understand what it means, and we've seen some applications. But now let me show you how to generalize this idea in Rn to other kinds of vector spaces, abstract vector spaces, which we hinted at in the last lecture. It turns out that something like the dot product does not exist in every vector space. But if it does, it is called an inner product, and the space is called an inner product space. The kinds of vector spaces that are used to represent quantum states in quantum mechanics are, in fact, inner product spaces. In a simple example, a quantum state may be given by a one-dimensional function called a wave function. These are usually complex wave functions, meaning that the scalars we allow come from the complex numbers. But just to keep things simple, think of real-valued functions over the real line. These form a vector space. Since if you have functions f and g, addition makes sense. You can add f and g. F plus g is a function. Multiplying by a scalar constant makes sense. But you can define an inner product very similar to a dot product now. Dot products are sums of pairwise products where the sum is taken over an index. But for functions like f of x or g of x, indices are like the argument x of the function. And since x can be any real number, a sum over indices of a pairwise product of components in the dot product is analogous to integrals over the argument x of the product of f of x and g of x. So the inner product of f and g is the integral of the product fg over x from negative infinity to infinity. This inner product has many analogous properties of the dot product. You can define the magnitude of a wave function as the square root of the inner product of f with itself. And then guess what? A version of the Cauchy-Schwarz inequality holds, which says the size of an inner product of two wave functions is less than or equal to the product of their magnitudes. A neat fact is that the Cauchy-Schwarz inequality turns out to be the fundamental mathematical idea behind something known as the Heisenberg uncertainty principle in quantum mechanics. That's the strange statement that says that the position and the momentum of a particle cannot both be specified exactly. In the proof of the Heisenberg uncertainty principle, the function f represents uncertainty in position, and the function g represents uncertainty in the momentum. Then the Cauchy-Schwarz inequality shows that there's a lower bound to their product because the associated inner product of these two functions turns out to be not zero. And that lower bound shows that position and momentum cannot be specified exactly. So the strange Heisenberg property of quantum particles is a direct consequence of the underlying mathematics of inner product spaces. There's another kind of product of vectors in Rn that is defined only in 3 dimensions. It is called the cross product. We'll define it both algebraically and geometrically. If you're given vectors u and v with components u1, u2, u3, and v1, v2, v3, the algebraic definition is given by some crazy formulas for the components. u2, v3 minus u3, v2, comma, u3, v1 minus u1, v3, comma, u1, v2 minus u2, v1. Now later on, when we learn about the determinant, we'll see where this formula comes from. But there is an easy way to remember this formula. Write u1, u2, u3 twice in a column, and v1, v2, v3 twice in a column next to it, like this. If you think of these as shoelace holes, form shoelace crossings in the middle 3 positions. The strings that go down to the right represent positive products, and the ones that go up to the right represent negative products. If you do this, you'll see how these crosses correspond to terms in the cross product expression. That's the algebraic definition. But now let's look at the geometric interpretation of the cross product. Unlike the dot product, the cross product of 2 vectors is a vector, not a scalar. So I have to tell you both its magnitude and its direction. The magnitude of u cross v is the length of u times the length of v times the sine of the angle theta in between them. Note how this differs from the dot product. The cosine there gets replaced by a sine here, and the dot product was a scalar. So the magnitude is the largest when u and v are perpendicular, and 0 when theta is either 0 or 180 degrees. In other words, when u and v are multiples of one another. The magnitude is never negative, as we always choose to measure the angle theta going from u to v, which is positive. The direction of u cross v is always orthogonal to both vectors u and v. Now there are 2 possible directions that could be orthogonal to u and v, so we have to choose one, and we always choose the one given by what's called the right-hand rule. We've referred to this in the past already. If your finger, your index finger, is pointing in the direction of the first vector, and your second finger is pointing in the direction of the second vector, then your thumb will be pointing in the general direction of the cross product. Here's another way to think about it. If you curl the fingers of your right hand in the direction from the first vector to the second vector, your thumb will be pointing in the direction of the cross product. Note how the order matters in both the algebraic and geometric definitions. If you look at v cross u instead of u cross v, you see the signs of all the components get reversed, and your thumb will be pointing in the opposite direction. So u cross v is the negative of v cross u. Let's do an example. Suppose I want to compute 450 cross 709. I can write out the shoestring diagram, and from this, I see that the first coefficient is 5 times 9 minus 0 times 0, which is 45, and the other components are computed similarly. So we obtain the cross product 45 minus 36 minus 35. We can use linear combinations and our new friends, the dot product and cross product, to help us describe lines and planes and hyperplanes. To specify a line L in R3, you can use a point P on the line L and a direction vector D that moves along L. Fixing the point P and adding scalar multiples of the vector D will move along this line, and every point on L arises in this way. So every point xyz on L must be of the form P plus Td, where T is a freely chosen scalar parameter. Once you choose T, the point xyz is determined. I like to think of the parameter T as time, and the vector P plus Td telling you the position of a bug at time t. At time t equals 0, you're at the point P. And if you set down tick marks at equally spaced time intervals, like time t equals 0, t equals 1, t equals 2, etc., you will see that the tick marks are evenly spaced along the line at the points P, P plus D, P plus 2D, etc. And if you plug in t equals -1, you'll move in the other direction. This description of a line gives us a way of describing what is happening with the components x, y, and z of a point on a line. Let's do an example. Suppose we want to describe the line through 1, 2, 3 in the direction of 4, 5, 6. If x is a vector representing a point on the line, then x must be of the form 1, 2, 3 plus t times 4, 5, 6, where t is freely chosen. This is called the vector form of the line. We can also write the vector x in components x, y, z. In that case, looking at the components of the vector form, we see that x equals 1 plus 4t, y equals 2 plus 5t, and z equals 3 plus 6t. This description of the line is called the parametric form of the equation of the line, or a parameterization of the line. Notice that if I had chosen a different starting point, I might have gotten a different parameterization. So a line can have many different parameterizations. This method for describing a line works in any dimension. All you need is a point on the line and a direction vector. You can also use a similar idea to describe a plane in Rn. Now you need a point P and two direction vectors u and v. Then you start at that point P and you add linear combinations of u and v to generate a plane through P. You can see this on the picture, how linear combinations of u and v will generate a grid on this plane. The coefficients of u and v will be scalar parameters that can be chosen freely. Let's call them s and t. Then any point on this plane must be of the form P plus s times u plus t times v, where s and t are real numbers. And this gives the vector form of the equation of a plane. All you need is a point and two directions. Now, if you want to write out the equation in components, you will get the parametric form of the equation of a plane. Let's do an example. Suppose you want to describe the plane through the point 1, 0, 0 in the directions 4, 5, 0 and 7, 0, 9. If the vector x has components x, y, z, then looking at the components of the vector form 1, 0, 0 plus s times 4, 5, 0 plus t times 7, 0, 9, we see that the vector x must be 1 plus 4s plus 7t, comma, 5s, comma, 9t, where s and t can be chosen freely as any real number. Notice that this description of a plane shows intuitively why this plane has two dimensions. It's because it has 2 degrees of freedom in the free parameters s and t. Also, a plane, like a line, may have many different parameterizations. In R3, we can use the dot product to describe a plane a slightly different way. If you know a point on the plane and a direction vector perpendicular to the plane, that's called a normal vector, that is enough to specify a plane. Let's see how. Suppose P is a point in the plane and n is a normal vector to the plane. If the vector x is any other point in the plane, then x minus p is a vector that must be perpendicular to n. So the dot product of x minus p with n must be 0. And I can distribute x minus p dot n as x dot n minus p dot n, and then move p dot n to the other side. And I'll see that x dot n must equal p dot n. This relationship is sometimes called the normal form of the equation of a plane. So any point x on the plane must satisfy this relationship. Let's do an example and find the equation of a plane through the point 1, 2, 3 perpendicular to 4, 5, 6. If vector x has components x, y, z and lives on the plane, then x, y, z dot 4, 5, 6 should equal 1, 2, 3 dot 4, 5, 6, which you can compute to be 32. Taking dot products, we see that 4x plus 5y plus 6z equals 32. This is the relationship that x, y, z must satisfy to be on this plane. Note that when I write an equation in normal form, like 4x plus 5y plus 6z equals 32, it's actually easy to see what the normal to the plane is, because you can just inspect the left side and read off the coefficients of x, y, and z. In this case, 4, 5, 6. These are the components of the normal vector to the plane. And if I change the point through which the plane passes, the right side of the equation may change, but the left side will stay the same. Recall our earlier example, the plane through 1, 0, 0 with direction vectors 4, 5, 0 and 7, 0, 9. Instead of describing it parametrically, we could have found the normal form of this plane by first finding the normal vector. To do this, let's take the cross product of 4, 5, 0 and 7, 0, 9. We actually computed it earlier. It's 45, minus 36, minus 35. Then the normal form of this plane is 45x minus 36y minus 35z on the left side, and 1, 0, 0 dot 45, minus 36, minus 35, which gives 45 on the right side. So the equation is 45x minus 36y minus 35z equals 45. Now what's the relationship between this form of the plane and the parametric form we derived earlier? If you take those parameterizations of x, y, and z in terms of t and you plug those in here, you will see that the t's cancel and they satisfy this equation as expected. So 45 times 1 plus 4s plus 7t minus 36 times 5s minus 35 times 9t does indeed equal 45. In this lecture, we've seen how to describe lines and planes using the notion of dot and cross products. These products are two examples of hidden structure of vectors that we now realize that we have and that are useful to us. In the next lecture, we will describe an object known as a matrix, which will give us a way to describe linear transformations. We shall see that matrix operations are built in a fundamental way on the dot product.